Hi everybody, welcome back. This video we're going to cover sections 710 and 711, and we're going to be talking about the history of the periodic table. And why was the periodic table put together in such a way that the periodic table was put together? And originally, as you can see, the periodic table was designed to represent patterns in chemical properties. So we wanted there to be some kind of pattern in repeating properties of elements. Originally, the elements were grouped together in groups of three elements that had similar chemical properties, and those were called triads. And that was Dobereiner's law of triads, where it basically said that the missing element's properties were an average of the other two. So, for example, he estimated strontium's mass to be 88 because he added calcium's mass together, which was 40, and barium's mass together, which was 137, and divided them by 2, and hypothesized that that middle element would have a mass that was average of the two. And strontium's actual mass, if we can look it up real quick, I think I have a periodic table here. Strontium's actual mass is 87.62, so not a bad rule, right? Same thing with sodium here, right? And lithium. Lithium's mass is 7, potassium's mass is 39. He averaged them together to get 23. Okay, so that was Dobereiner. He was the triad man. He originally grouped elements together in groups of elements that had three similar properties. Excuse me. Okay, so Mendeleev came next, and Mendeleev put the elements in order of increasing atomic mass and used several other properties to predict an unknown element at the time. So he used their oxide formula, their chloride formula to predict the properties of this unknown element and left a blank for its position. Okay. The big difference between Mendeleev's periodic table and ours is that Mendeleev was in order of increasing mass. Ours is in order of increasing atomic number. That's one of the major differences. The more important section here is section 711. Section 11 introduces the Aufbau principle, which basically states that electrons are added to the orbitals and sublevels and energy levels outside the nucleus, just like protons are added one by one to the nucleus. So as protons are added to the nucleus, electrons are added from lowest energy to highest energy outside the nucleus. Aufbau literally means building up. Shh. Okay. So a couple rules. We're going to be constructing orbital diagrams and writing electron configurations. First of all, electrons fill from lowest to highest energy. Pauli exclusion principle holds. If you have an orbital that has 2 electrons, one must go up, the other must go down. Okay? You cannot have them both spinning the same way, or they would have they would have all 4 sets of quantum numbers. Hold on. Sorry. So anyway, you need to know how much each sublevel can hold. You need to know S can hold 2, and P can hold 6, and D can hold 10, and F can hold 14. And you need to be able to apply Hund's rule. Hund's rule states that any orbital must have 1 electron within a sublevel before any other orbital can have 2. So everybody needs 1 electron within a sublevel before anybody could have 2. He said that it's more energetically favorable to have more unpaired electrons in a set of degenerate orbitals, which is within the same sublevel. And when you do put these 1 in any box, 1 in any orbital, the electron spins up. Okay, so here's Hund's rule, maybe in words that you can write down. The lowest energy configuration is the one having the maximum number of unpaired electrons, which basically means, again, every box within a sublevel, every orbital gets 1 electron before any one can have 2. Everybody gets 1 before anybody can have 2. That is Hund's rule. Okay? Okay, so when we say we fill from lowest energy possible to highest energy level, we kind of use this diagram over here. I like to use this diagram where we start at, I'll redraw it for you as best I can, but we start down here at 1s, whoops, and then up here above it is 2s, and next to 2s is 2p. And then we have 3s, 3p, 3d. And then up here we have 4s, 4p, 4d, 4f, etc. And then 5s. S's go over s's, p's go over p's, d's go over d's, f's go over f's, and g's go, oh boy, over g's. Okay, so then what you do is you fill on the diagonal. So your filling order is going to be 1s goes first, and then 2s, and then 2p, and then 3s, and then 3p, and then 4s. So this ensures you fill the lowest available orbitals first. This is your filling order, and you don't need to memorize it. That's just how you do it because it's right there. So if we go back here, we can write, I think I had a spot, whoops, for your final filling order. Okay, so your filling pattern is then, hopefully I can do this here for you, is 1s. And 1s can hold a total of 2 electrons. And then 2s, which can hold 2. And then 2p. P has 3 orbitals, which each can hold 2, so p can hold 6. And then 3s, which can hold 2. And then 3p, which can hold 6. Now, if we add these up right now, this is 10 total electrons. And then we go one more. After 3p comes 4s. And that is another 10 electrons. So we're already up to the first 20 elements here, right? Up to neon. That's 4s. And then we have 3d, 10, and then 4p, 6. And then I'll see if I can scroll down any more. Nope. After 4p comes 5s, right? Let me see, 4p6, 5s, and then 4d. So you just keep filling along the diagonal. And after 4d10, we go back up. 5p6, 6s2, etc., etc. Okay, so this is our general filling order from lowest to highest, and this is what we'll do when we write electron configurations, just like you're going to see in this example. Okay, we're not going to do, I'm going to do 2 and I'll have you do 2. So number 1A says write the electron configuration for boron. So boron is B. And boron has 5 electrons. So we're going to fill from the lowest first. So first we're going to do 1s, and 1s can hold 2. So we'll put 2 there. And then we have 3 to go, so then we'll go to 2s. 2s can hold 2. That gives us 4 total electrons. And then we go to the next available sublevel. Whoops, not 3. 2p. Now p can hold 6, but we only need it to hold 1, so it would just be 2p1. So that's your electron configuration for boron. 1s2, 2s2, 2p1. I'll do vanadium down here for you, and you can do for me sulfur and iodine. You can go ahead and try to write the electron configurations for sulfur and iodine. So vanadium, if we look it up in the periodic table, I think its atomic number is 25, but I just want to be sure. 23. Phew, good. Okay, so vanadium has 23 electrons. I'm just going to write that down for me to keep track. So I go my filling order. Remember, 1s2, 2s2, 2p6 is 10. Then you go 3s2, 3p6, 4s2, that's your 20. Now I need 3 more. Now the next place we fill after 4s2, if we go back to this page, I always write this diagram on my paper, but after 4s2 we go to 3d10. Now D can hold 10, but I only have 3 electrons left, so it's 3d3. While we're here, let's talk about valence electrons. Remember, valence electrons are the electrons in the outermost energy level. And I know we've talked about this in class. Instead of saying outermost energy level, I want you to say the last N, the last principal energy level. Because often I'll ask students, how many valence electrons does boron have here? Remember this guy was boron? And students will simply look at the last number and say, oh, boron has 1. But remember, it's not in the last sublevel, it's in the whole last principal energy level too. So not only do you have p electrons, but you also have s valence electrons there. So boron has 3 valence electrons, okay? Same thing with vanadium here. If we look at this, if you were to just look at this, you might go, oh, the last energy level is 3. The highest most N is 4, right here, right? So vanadium really only has 2 valence electrons, because those are the only electrons in the 4th energy level. So you look for the outermost biggest number, okay, the outermost energy level, the outermost N, and then you count up all the electrons that are in the N. I'd like you please to do C and D here for the valence electrons for vanadium and iodine. Okay, now the shorthand notation's a little bit confusing. Let's look at vanadium. When you do the shorthand notation, like for vanadium, you look at the periodic table and you find the noble gas that comes before vanadium. So vanadium's 3. I want to go in the row before it. The noble gas is argon. Okay? So vanadium is argon's configuration, because argon was 18, basically plus 5 more electrons, right? Argon is 18. So vanadium is 18 plus 5 more electrons. So really all we have to add on is the 5. But the hard part is where to add them on. And the periodic table helps us with that as well. If we look at the periodic table, okay, the noble gases are called the P block. And the row is the N that is filled. For example, Ne is in the second row, which means it has filled the 2p sublevel. So Ne would end at 2p6. And argon would end at 3p6. So this really ends, this configuration here really ends at 3p6. So we just have to add on what comes after. The 5 electrons come after, whoops, so it will be argon. After 3p6 comes 4s2, 3d3. There's our argon plus our 5 electrons. All right, I want you to try the shorthand notation for the other 3, and we'll come back and hopefully one more video we should be all set. Bye-bye, guys.